So far, the topics covered in the lecture Statistical Physics 1 were rather formal. We developed the notion of the partition function and the entropy, so far just motivated that we wanted to calculate means of variables. In what follows, we will see that our definitions are much more powerful. So let's get back, and what we saw in the last clip, that the partial derivatives of the entropy define the equilibrium of two systems. The entropy was therefore defined as a function of n, e, and v. Now let's have a look on these partial derivatives. The first partial derivative, the partial derivative with respect to the number of particles, is describing the equilibrium in the number that we defined as the chemical equilibrium. Let's define this partial derivative as Kb times alpha, where alpha is the affinity. The second equilibrium we considered was the equilibrium in energy, or the thermal equilibrium. The partial derivative of S with respect to E we equal to Kb times beta, which is equal to, and that is what we will see in a moment, 1 divided by T. The definition seems also reasonable from the experiment that we proposed. In this experiment, we brought together two systems in contact with interchange energy. After we separated the two systems again, we asked, is the energy of system 1 unchanged? From our daily experience, this could only be if the two systems would have had the same temperature before. Our new definition of beta we also could use in the prior equilibrium state, and saying that the derivative of the entropy with respect to n is given by minus Kb beta mu, or that the derivative is equal to minus mu divided by T, where mu is the chemical potential. Lastly, we consider the final derivative describing the equilibrium in the volume, or the mechanical equilibrium, and what we found is that ds dv is equal to Kb times gamma, where gamma is the expansion coefficient, or using again the definition of beta, the derivative is expressed as Kb times beta times P, or is equal to P divided by the temperature, where P is the pressure of the system. Let's use this latter definition in the example of the ideal gas. We obtain P divided by T is equal to the partial derivative of S divided by V, which we calculated to be Kb times N divided by V. Rearranging, we obtain P times V is equal to N times Kbt, which is the ideal gas law. We may also consider our definition of the temperature, which says that 1 divided by T is equal to the partial derivative of S with respect to E. And looking back on our evaluations of the ideal gas, there we found that this is equal to 3/2 Kb N divided by E. Rearranging, we calculate the total energy divided by N, the number of particles, which is nothing else like the mean energy per particle, is equal to 3/2 Kbt. What we just derived is the equipartition theorem, telling that the mean energy per particle is given by 1/2 Kbt times the degrees of freedom the particle lives in. Here you see the full power of the theory that we developed. We started by calculating the partition function just as a means of calculating mean values of observables. Yet what we see, this partition function is much more powerful and can lead to the equation of states as we see it here in the case of the ideal gas and the ideal gas law. Now this power we will further develop and look for further applications of the theory of statistical physics. All the definitions I gave for so far are given for the entropy. Sometimes it's more convenient to not talk about the entropy, but rather about the chemical potential S hat. The partial derivative of S hat with respect to n is equal to gamma. The partial derivative of S hat with respect to energy is equal to beta. And the partial derivative of S hat with respect to V is equal to beta p. So let's wrap up our definitions. The entropy is defined by its three state variables, n, e, and v, and associated to each of the state variables is the parameter that is describing the partial derivative of the entropy with respect to that parameter. Those are called the conjugate variables. For n, it's the affinity alpha. For e, it's the inverse temperature beta. For v, it's the compressibility or the pressure of the system. Now the state variables on the left, n, e, v, and also s, are extensive variables. Extensive means they scale with their size, whereas the conjugate variables of the microcanonical ensemble are intensive variables. They are independent of the size. Doesn't matter whether I have a very small sample or have a very big sample, this temperature can be the same. What extensive means, we can work out a little bit more formal in terms of the entropy. Extensive in the terms of entropy means if I have an entropy of a system where I have lambda times n particles, lambda times e energy, and lambda times v volume, this entropy is equal to lambda times the entropy of n, e, and v. In the next step, we look on the differentials of the entropy, which means we're interested how does the entropy change if we change any of its parameters. ds of n, e, and v is total differential, which is partial derivative of s with respect to n times dn, the partial derivative of e with respect to e times dE, and the partial derivative of s with respect to v times dv. Now, using our definitions before, this can be transferred into the so-called general equation of state. Now, usually the general equation of state is stated in energy. So we can solve the above equation with respect to the energy, by which the energy is now a function of ns and v, and that is given by the sum of three terms, where the first term is describing the thermal energy, heat, that is applied to the system. The second is the mechanical work applied to the system. And the third is some chemical energy. If we now further assume that we deal with a closed system, which means that there is no change in the number of particles, dn is equal to 0, we obtain the equation dE is equal to dQ minus dW. Nothing else like the conservation of energy. So the change in energy is given by changes of the thermal energy that you put into the system minus the work that you take out of the system. Further, it's interesting to look on the definition of heat, because this is one way how experimentally you can measure the entropy. The entropy is then given by the integral on dq divided by t.